Hello, my name is Ignacio Encinas Rubio, and I'm gonna briefly explain my Summer of HPC project. We have been working on an MPI version of FMM. This is important because n-body simulations play a fundamental role in scientific research, and they would not be possible without the fast multiple method. FMM is relatively complex, but we can build some intuitions through the core ideas behind it. As we want to avoid computing pairwise interactions because the complexity of doing so is quadratic, we have to group particles together somehow. We group them by dividing space into small cubes up to an arbitrary depth. Every cube on every level will be represented by something called multiple. The multiple encodes the effect of every particle within the box. Once we have constructed the smallest cubes, we have a sense of distance. This so-called distance in grid units will determine when to compute pairwise interactions and when to compute the interactions through multiples. We will name these two types of interactions as near field and far field, respectively. FMM uses two tree-like structures that encode these multiple representations. The first one is built from the lowest level. We construct the multiple representation for a parent box using the representations from its children. These multiple representations will then be translated into local ones and used to account for the far field interactions. Lastly, we construct the local moments tree in a downward manner. At this point, we have completed the preparations and we are ready to make actual computations for the far field. As we are not that interested on large systems, we have to carefully design a communication schema for minimum overhead. It is important to notice that translating FMM into MPI is not trivial at all, as there are many nuances. Because of this, we decided to focus on the near field as it is much simpler to parallelize. Our goal was to measure the scalability of small workloads for the near field starting from a naive implementation and improve it iteratively. Our initial implementation used an MPI reduce. We shared a lot of redundant information, but it allowed us to make initial measurements without having to assign workloads for each MPI process. Even though we knew this wasn't efficient, we were surprised by how slow the communication was and the large difference between the distribution time and the reduction time. We came up with three possible explanations. First, the message size is too big and we will see great improvement after trivially reducing it. Second, load imbalance appears when scaling up in the number of processes. And third, MPI reduce behaves especially bad and avoiding it will bring significant speed up. We started by measuring the load distribution and discovered that there was no load imbalance that could explain the bottleneck as we can see in the right plot. We proceeded accordingly with the other ideas and reduced the redundant communication and computation. Significant speed up was expected from this, but it just wasn't there. Despite not getting the desired results, there are some good news. The communication latency for the near field can be hidden by the far field computation. The initial data distribution is surprisingly performant. Good efficiency is within reach for heavy workloads, and there is much work left to do. On the other hand, we are still very far away from the long-term goal, and more work is needed in order to understand the bottleneck. I would like to thank the whole Summer of HPC team for making this possible, and Ivo for his hard work and continued support.